So we're given that y equals f of x and y equals g of x are as shown below. Which of the following statements about the function, which is the product, is false? So that says there's 5 statements. 4 of those statements are true. 1 of them is false. So the statements are, you're continuous at 1. There's a jump discontinuity at 2. There's a jump discontinuity at 3. There's a total of 2 discontinuities between 0 and 4. And the left-hand limit at 0 is 12, and the right-hand limit at 4 is 2. All right. Which statement is false? C? Good. That is correct. It's not a jump discontinuity at 3. It's a removable discontinuity. That's a different type of discontinuity. Now, what happens is, you might say, but there are jump discontinuities in f and g. But yeah, but we're not looking at f and g, we're looking at f times g. How do you check? You check the limits. And as we come in from, say, the left, at 3, we're coming into what numbers? 2 here and 3 here. 2 times 3, 6. From the right, 2 here, 3 there. 2 times 3 is 6. So the left and right limits agree, but if you plug 3 into the function, you get 16. So that was a false statement. All the others are true statements. Now, I mentioned here there's a pro tip. Don't spend a lot of time justifying why things are true. You don't have to do that for multiple choice problems. Your goal is to quickly find which one is false. In some sense, you've got the fun job. The people writing have to come up with why everything is true. You just have to find why one thing is false, and then go. So, all right, so there's our review problem. And we're not doing a quote today. We're going to talk about a learning technique in some sense. This is called rubber duck debugging. So what does this entail? Well, it involves rubber duck. So you have to imagine that you have a rubber duck. So maybe you have a rubber duck available. And this is something that's used by computer programmers. And what happens is that sometimes, hard as this might be to believe, you're trying to do something and you get stuck. So the rubber duck debugging procedure says, find a rubber duck and start explaining your code to the duck. Say, okay, this is my code. This is what I wanted to do. I start by doing this, which does this, and this happens. And you explain the whole process. And in the act of explaining things, there's a great aha, I see my problem. Now I can fix it. And so this is a great way to sort of overcome being stuck. It's a much better technique than just sitting there. Sitting there is not effective. So the nice thing is, it doesn't just work for programming, it works for other things, like math. And if you're stuck, just start explaining things. Explain the problem. Explain your approach. Explain your steps. Explain what should be happening. And oftentimes, the same thing that happens with programmers. You'll say, oh, I see the issue. I can fix it. Now, rubber ducks work great. Even better, humans. Try talking to other people. This class, it turns out, is full of humans. And so you can try working. And I often find that explaining things is one of the best ways to learn things. And thankfully for me, I've been explaining math now for a while. I feel like I'm finally getting the hang of it. And so this is a good approach, a good approach. All right, that's our learning idea for the day. Now on to the topic for today. And I know it's kind of sad to say this, but we're nearing the end of limits. Or I suppose you could say we're reaching our limit on limits. So what's the last thing for us to talk about? Now, we are going to keep using limits for a few more lectures, But the goal sort of for next week is to be like, we don't ever want to see limits again. So we're going to try to say, let's figure out how to do stuff without them. All right, so the last thing to talk about are limits which involve infinity. And if I can spell the word involve, there we go, involve infinity. So I suppose we have to stop for a second and say, well, wait, what is infinity? Now, you might say, well, it's just like a really big number, right? Well, kind of. When we say something is infinite, we really don't say it's a number necessarily. A better way to think about it is sort of infinity means that we are unbounded. We're going to infinity. As Buzz Lightyear would say, to infinity. But then we can't go beyond it. We just keep going towards it. So that's the idea. Infinity is this notion of things are unbounded. Now, there's two ways infinity can show up in our problems. One way that infinity can show up is that infinity can be in our inputs in some sense. And so for that, we're saying, well, what's happening to our function as we let our inputs go towards infinities? Now, in our class, we're going to have two types of infinity. There's a positive infinity and the negative infinity. So when we say x is going to infinity, what we really mean is that x is just growing unboundedly in the sort of positive direction. So we're getting larger and larger. So here, when we talk about what's this limit, is what happens to f of x as x gets arbitrarily large positive. Now, it might not converge. Not all limits do converge. But if it does, then we give this a special name. So if the limit as x goes to positive infinity of f of x is some value L, then y equals L is a horizontal asymptote. So asymptote means we're approaching it. Okay, similar idea for negative infinity. What's the only difference as we go to negative infinity? Yeah, so x gets large, but not arbitrarily large negative. It's arbitrarily large, not arbitrarily large positive, arbitrarily large negative. We're heading in the opposite direction. We're heading, it's a large value, but it's a large negative value. And again, same thing. If the limit as x goes to minus infinity of f of x equals L, then y equals L is a horizontal asymptote. Same kind of idea. So let's look at a couple of really simple examples, and we'll get to what our other situation is. Well, let's try our function f of x equals e to the x. What happens to e to the x? So as x goes to infinity, e to the x, as x goes to infinity, as x goes to negative infinity, e to the x. What happens? So as your input gets large positive, e to the x, the function, does what? It gets big, arbitrarily big. So you can either say it's infinity, sometimes people will say it does not exist, either one. When we say something's infinity, it just means it's getting arbitrarily big. I would say I would lean towards infinity. What happens as x goes to negative infinity of e to the x? It goes to 0. So in particular, this is an example where on one side you blow up, but on the other side, so over here it's getting big, but on the other side it's getting small. It's tiny. So we have different behavior. So you have to check both positive infinity and negative infinity if you're asked to check for horizontal asymptotes, because you can have different behavior to the two different directions. So we have to keep that in mind. All right. Let's see. What are some things we can do? All right. Let's make up an example. Why not? It's always fun to make up examples. Anyone have a favorite quadratic polynomial? I'll start it off. X squared. Three x. One more number?
0.
6. Downstairs. How about we say 2x squared minus x plus 111. Just in the interest of time. All right. Are there any horizontal asymptotes? All right, that's the question I want to ask. So what do we do if you want to find horizontal asymptotes? Well, the answer is we take a limit. X goes to infinity of f of x. And we see what happens, and then we're going to take a limit as x goes to minus infinity of f of x and see what happens. Let's just do the top one first. So this will be the limit. X goes to infinity. And let's just write it in. It's not piecewise, so we say, okay, it's always the same function. X squared plus 3x plus 6. 2x squared minus x plus 111. Well, our mantra when we're doing these limits is to say, well, first plug in. And then see if you have to do more work. So as x is getting big, so that's what we mean when we say x is going to infinity, what's happening to our numerator? It's getting big. Now, think about these three terms, x squared versus 3x versus 6. Which one of them is the important one? I'm putting important here in quotes. Important. Which one drives it? The x squared. Okay, so, all right, now downstairs, what's happening? It's also getting big. So we say, aha, it's going to like infinity over infinity. And as we all know, infinity over infinity equals more work. Yes, it's like the 0 over 0. The problem is, it's an ambiguous thing. Indeterminate. So like, okay, so we have to do more work. Now our problem is things are getting big. If you think about what we do with limits, we say, oh, we have a 0 over 0 happening. Usually what the more work involves is to say, let's get some cancellation. So something's causing the 0 upstairs, something's causing that 0 downstairs. Let's find a way to cancel them out and then see what happens. So that's 0 over 0. Same philosophy. Something's causing it to be big upstairs. Something's causing it to be big downstairs. Let's, quote unquote, cancel it out. And the way I often put this is, let's apply the brakes. We're going too fast. We need to slow down. So, how do we slow down? We say, what's causing the growth? What's the biggest growth thing on the top? The x squared. What's the biggest growth thing on the bottom? Yeah, the x squared. The 2 is a 2. That x squared. Okay, so we say, aha, let's apply the brakes. So to do this, we're going to start, and we have our same function that we're taking the limit of, because we can't change the function, we can only rewrite the function. So when I say apply the brakes, I want to be very clear about what I'm doing. I've identified what's causing the biggest growth. So I'm going to divide out by the biggest growth. Because I want to sort of hit that sweet spot. I want to slow things down so it doesn't get arbitrarily big. I also don't want to slow things down too much so that it goes arbitrarily small and goes to 0. I want to sort of cancel out exactly the growth. So that's why identify what's causing the big term, divide out by that on top and bottom. Well, what happens? We have the limit as x goes to infinity, and now you bring that x squared into each term. So you have a 1, because x squared over x squared is 1, a 3 over x, a 6 over x squared. Divide that by a 2 minus 1 over x plus 111 over x squared. So it's the same function written in a different way. But is it written in a useful way? Now let's plug in infinity. Now what do we mean by plug in infinity? We just say what happens as x gets big. So as x gets big, 1 stays as 1. What happens to 3 over x? Goes small, goes to 0. 6 over x squared? Goes small. 1 over x? 111 over x squared. Even if it's 111? Yeah. I could have like a gabillion. But if I divide by x squared, it's still going to go to 0. Actually, I couldn't have a gabillion because that's not a word. But if it were, it'd be a good point I just made. So, do we have a problem anymore? No. We've slowed things down. We don't have infinity over infinity. We don't have 0 over 0. We have what? 1 over 2. So that says a horizontal asymptote of y equals a half. Now that's as we go to positive infinity. What about negative infinity? Well, you do the same thing. Now notice we can do the exact same process. There wasn't really anything that required the sign. So we could just say, oh, this is the same as the limit as x goes to negative infinity, applying the same breaks as we did over there. 3 over x, 6 over x squared, 2 minus 1 over x, plus 111 over x squared. And as x gets to a big negative number, what happens? Well, what happens to 3 over x? 6 over x squared, 1 over x, 111 over x squared. So we end up with a half. Now, looking at this, you might say, oh, so there's just one horizontal asymptote. It's y equals a half. It's for both positive and negative infinity. And you might say, didn't you basically just do the following? Looked at the leading coefficients? Yes. That's what it boils down to. And in this case, in essence, that's what will always happen, is if what's your rate of growth match. So in our case, the rate of growth were both x squared. If they both match, top and bottom, then you just pay attention to what's in front. Now, if there's a mismatch, it will either blow up or go to 0. So, all right, let's see. I think we have one that we should have you try. Your turn. Find horizontal asymptotes for the function 7e to the x plus 3 over 1 plus e to the x.
Positive infinity, it goes to 7, and negative infinity, it goes to 3.
Two different ones? You're right. So, as we go in different directions, we're going to get different values. And for positive infinity, again, it's that blowing up. E to the x is driving the growth, so you divide out by e to the x to slow it down, so you end up with something that goes to 7. Now to negative infinity, you don't have to do anything, because nothing's blowing up. Because as you head towards negative infinity, e to the x is getting small. So you just plug in, again, when we plug in infinity, You can't actually plug in infinity. You just say, well, what's happening as we're going to infinity? And so you say, as x goes to negative infinity in this case, e to the x gets small, so we're going to 3. All right, so we can have different answers even for relatively benign looking functions. Okay. Here's another problem to look at. Find horizontal asymptotes for f of x equals the square root of x squared plus 4x plus 7 subtract x. So we have to check two directions. Positive infinity, negative infinity. Which one do you want to do first? Okay, good. You want to do the hard one first. I salute you. Most people would want to do the easy one. So I'm glad. I'm glad. You're saying positive. Yeah, good. You're an optimist. I like that too. All right, so let's look at as x goes to positive infinity. So we're going to take the limit as x goes to infinity of the square root x squared plus 4x plus 7, subtract x. Now, we start by plugging in. What happens to our first term? That square root of x squared plus 4x plus 7. What's it going to do? It's going to get big. It's going to get arbitrarily big. So we say, that first term is getting big. What about this second term? Well, it's also getting arbitrarily big, but we're subtracting it. So we're going to infinity minus infinity. All right. Well, what is infinity minus infinity? 0. More work. More work. No, infinity minus infinity does not equal 0. I know, very tempting, because that just seems right. It seems like what God would intend. But unfortunately, you have me as a teacher. So, but actually the problem is infinity minus infinity is sort of like, how do they relate? Are they exactly the same or are they off a little bit? And if they're off a little bit, how much? So we got to figure that out. So what do? We have a problem. We can't slow down the top and the bottom because there is no bottom. Well, I mean, there is. There's always, you can put a 1 downstairs. But there's nothing to slow down downstairs. But there's a clue here built into this problem. I don't know if you noticed it, but I saw something. It was this square root. When you see square roots, what does that suggest? Conjugation. Yeah, good stuff. Conjugation. All right, so let's do the conjugation. So this is our limit as x goes to infinity. And we have the same thing. I'm just copying it down. Not changing anything yet. I'll put the over 1 just to emphasize. So the conjugate says, change the sign. And now, so instead of subtract x, you add x. You have to multiply both upstairs and downstairs. We can't change the whole function. All we can do is write it in a different way. So by multiplying the same thing top and bottom, we're multiplying by 1. That's the same function, different way to express that. Okay, now why do we do this? Well, conjugation is great at getting rid of square roots. So if you see square roots, that's why we think, hey, maybe conjugation. So this becomes the limit as x goes to infinity. Well, what happens upstairs? You get rid of that square root, it becomes x squared plus 4x plus 7. And what happens to the last terms? Minus x squared. What about the other terms? Well, they cancel. That's by design. This and that, these two pair of terms, are exactly the same but opposite signs, so they cancel each other. All right, downstairs, well, it's the square root of x squared plus 4x plus 7 plus x. Does anything happen upstairs that we might be able to take care of right away? Yeah, it can cancel some x squared. Okay, now, progress, right? So, we have a limit as x goes to infinity, 4x plus 7, divide by the square root of x squared plus 4x plus 7 plus x. All right, we did something. So we should, of course, say, maybe we're done. Let's plug it in. What do we get? Upstairs, what's happening to this expression? It's big. What about downstairs? Big. So we have an infinity over infinity, which means more work. See, people probably are like, oh, wait a second. Infinity over infinity should have been 1, but infinity minus infinity should have been 0. So is this a proof that 0 equals 1? No. It's a proof that we need to do more work. That's what we've proven. Okay. All right. So what's the work that we do? What do we need? We need to slow it down. Apply the brakes, if you will. The upstairs is probably the easiest to see. What's causing the growth? The x. So how should I slow it down? Divide by x. So we say, okay, let's slow things down. Limit as x goes to infinity. We're going to copy this again. Square root x squared plus 4x plus 7 plus x. Multiply top and bottom by 1 over x. That's us applying our brakes. Okay. I hope we leave room for the other half of this problem. Okay, so multiplying the top, we get 4 plus 7 over x. Now I'm going to pause here and say we're basically in the end game now. Because that numerator is in the sweet spot. What is the numerator going to do? The 4 plus 7 over x. What's happening to that? Well, the 7 over x is getting smaller, but the whole thing is going to be 4. And do you know what's nice about 4? It's not 0, and it's not infinity. And once you're outside of it's not 0 and it's not infinity, you're like, I'm done. Now I just have to figure out what happens. So there's no more manipulations. It's just like, we know we're in the end. Okay, the x times 1 over x on the end, that's the easy part. How do you move this inside a square root? So you're telling me that 1 over x is the same as 1 over the square root of x squared? It is. In this case. But why in this case, and when would it not be true? What's special about what we're doing?
It's infinite.
That's not that it's infinite, but it is. There's certainly something going on here. It's not so much that it's infinite, but what kind of infinite? Positive infinity. So we want x to be a big positive number. So if I take x to be a big positive number and I square and square root it, I get back x. But what if I were going to a big negative number? Just theoretically. Just theoretically. Would this be true if I were heading towards negative infinity? No. What would you have to do to fix it? You'd have to throw in a negative sign. And you're like, they would never do something like that. There's a quiz problem for next week where they do something like that. And that quiz problem comes from an old exam where they did something like that. The students did not appreciate it. So just be mindful. Okay, so we're going to move it inside. You are correct. When we're approaching positive infinity, we are good to go. 1 over x becomes 1 over square root of x squared, which means that when we put it inside the square root, it's like dividing everything inside the square root by x squared. So 1 plus 4 over x plus 7 over x squared. Now, we ask, what happens to our pieces? What's happening to 7 over x? Goes to 0. 4 over x. 7 over x squared. So, all together, upstairs, 4. Downstairs, square root of 1 plus 1, which is 2. So we get 2. So, y equals 2 is a horizontal asymptote as x goes to positive infinity. Are we done? No. Now what do we need to look at? Negative infinity. Oh no. Oh no. What could happen here? Limit as x goes to negative infinity, square root of x squared plus 4x plus 7 minus x does what? What's happening to that first term? Square root of x squared plus 4x plus 7. What's it doing? It's getting big. Yes? What's happening to the minus x? It's getting big because we're subtracting a really big negative number. It's actually getting big positive. And infinity over infinity plus infinity means we're done. So, if they're the same sign, you're done. If they're different signs, infinity minus infinity, that's more work. Infinity plus infinity, done. Done. Okay, so there is no horizontal asymptote for the left-hand side. So there's only one horizontal asymptote. So that's good. That's good news. Now, we talked about horizontal asymptotes, but we should talk about the other type of asymptote as well. Okay, so the other type of asymptote is that infinity can show up in our output. So we talked about how infinity could be in your input, but infinity could be in your output as well. So these are called vertical asymptotes, and they're ones that you're somewhat familiar with. So probably the easiest one that you will recognize, y equals 1 over x. What happens to 1 over x as x gets close to 0? It blows up. So the limit as x approaches 0 from above of 1 over x, what does that become? Infinity. What's the limit as x approaches 0 from below of 1 over x? Negative infinity. What's the limit as x approaches just 0 of 1 over x? Does not exist. Because they have different situations. So what's causing vertical asymptotes? Essentially, you should say divide by 0 is your philosophy. Now, I'm going to make a comment here that we've talked about dividing by 0 before. And there's sort of two things that can happen when you divide by 0. So one thing that can happen is you get the 0 over 0. Now, what does 0 over 0 often become? Well, it's always more work, but in particular, at the end of the work, what does this lead to? In terms of what we talked about last time, starts with an R, removable discontinuities. Not 100% of the time, but most of the time that we see 0 over 0, that's removable discontinuities. That's what we should think. Now, what if you get a non-zero number divided by 0? So like 2 over 0, 5 over 0. What's that doing? Well, this is when you get that vertical asymptote. Because what happens is if you have a non-zero number divided by 0, essentially you have like 1 divided by a really tiny number. Dividing by a tiny number is the same as multiplying by a huge number. So it's causing things to blow up. So you should think of it as that's our vertical asymptote situation. Now, these are not 100% guaranteed, but this is the intuition you should have. When you're looking for vertical asymptotes, I'm looking for a non-zero divided by 0. I'm looking for removable discontinuities. I'm looking for 0 divided by 0. All right, let's see. We got a few minutes left. Here's a problem. Find the limit as x approaches 1 of 3x squared minus 7x plus 5 over x cubed minus 2x squared plus x. We'll do this one together. What's happening? Well, first thing is plug in 1. When you plug in 1, what happens upstairs? You get 3 minus 7 plus 5, also known as 1. Downstairs, 1 minus 2 plus 1, also known as 0. So this is blowing up. Now, are we done? No. But now we know things are blowing up. We're going to be a little bit more precise. We want to figure out how is it blowing up. Is it blowing up to positive infinity? Is it blowing up to negative infinity? Or something else? Maybe the two sides have different behaviors. So we have to be a little bit more careful. All right, so let's take a closer look at this expression. Let's see if we can't clean it up. I really don't care about the upstairs. It's the downstairs that's causing my 0. That's where I'm going to put my energy. Is there anything I can do to rewrite that? Yeah, pull out an x. Then you get x squared minus 2x plus 1. Is there any way to write x squared minus 2x plus 1? It does factor. How does it factor? X minus 1 squared. All right. So, let's think about our situations. Okay, maybe we can start by doing one-sided limits. When in doubt, one-sided limits are helpful when you're trying to make decisions. And the way I like to think about this is I like to say, okay, 1 minus, this is a number just below 1. And if it helps, I can think of like 0.99. Think of an example. Something slightly smaller than 1. I know it's going to blow up because I see a non-zero over 0. What I want to figure out is how is it blowing up? So I'm going to channel the oldie song, right? I saw the sign. And here, it's positive or negative. And say, okay, let's think about the sign. The upstairs is going to be close to 1. So this is close to 1. And the downstairs, okay, we have something close to 1. This is our intuition. What's happening to x minus 1 squared? So 0.99 minus 1 squared. It's close to 0, but how is it close to 0? Positive or negative? It's going to be a positive because you're squaring it. So this is a small positive. So the key is that small part is going to drive your behavior for your asymptote. So am I going to be going to positive infinity or to negative infinity? Because all these are positive, and then this part is also positive. Everything's positive, so this is going to positive infinity. Now if we approach from above, okay, so now think like 1.01. Well, what happens there? What do we get? The top is close to 1. X is close to 1. X minus 1 squared. What happens to that case? It's still a small positive number. So what's happening? Am I blowing up to positive infinity or negative infinity? It's still positive infinity. So this is a case where both sides blow up to positive infinity. So this limit does exist. And we would say that it's infinity, because on both sides it's blowing up in the same way. So the limit here is infinity. All right. Okay. This is a lovely problem, but I think we're short on time. So let's go and move. Any questions? What do you mean by all real numbers? Sure. Now there are limits that do some really weird things. I'll point one out to you really quickly. What happens to the following? What's the limit as t goes to 0 of sine 1 over t over t? All right, if you weren't paying attention, what do you think your answer is? It feels like 1, right? Because this feels like sine of blah over blah. But is it sine of blah over blah? No, no blah. See how it's 1 over t? That's not 1 over t. What's happening to this? Well, what you should think of is you have a function that really has two pieces. 1 over t and sine 1 over t. Now, the sine of 1 over t, just this part by itself, that has this weird property. I'm just going to sketch on the right-hand side. That's one that goes up and down infinitely often. This 1 over t, what does that do? Well, it blows up. When you combine the two together, the way you combine them is you do the following. You sketch 1 over t minus 1 over t. Now that's not the curve. And then what's happening is this part is what's going to happen to, you're going to squeeze this in between these two curves. So you're going to go up and down like that. So as t is going to 0, what number are you approaching? And the answer is yes. You're approaching all of them. And so in some sense, you're approaching none of them. So things can get very, very weird. All right. We have, I think, 1 or 2 minutes left, maybe. So, which of the following statements is false? Here's this function, absolute value of x cubed minus x over x cubed plus x squared minus 2x. One of these statements is a false statement. So you have your options. Negative 2 is a vertical asymptote of your function. 0 is not a vertical asymptote. 1 is a vertical asymptote. 1 is a horizontal asymptote. Negative 1 is a horizontal asymptote. It's what? C? Maybe. Ah. You're right. It is C. X equals 1 is not a vertical asymptote. It's removable. All right. Thank you.